Welcome to solverfy.
For this problem on the topic of oscillators, we are told that 6% of the mechanical energy of a damped harmonic oscillator is lost every cycle. And we want to know firstly, what percentage does the frequency differ from the natural frequency 1 over 2 pi square root k over m? And we want to know after how many periods will the amplitude have decreased to 1 over e of its original value. Now the energy of the oscillator is all potential energy when the cosine factor is 1, and so the energy E is equal to a half k a squared, which is all elastic potential energy, which we can write as a half k a naught squared e to the minus bt over m. The oscillator is losing 6% of its energy per cycle, and we can use this to find the actual frequency and then compare to the natural frequency. So the energy after one period, t plus capital T, where capital T is the period, is 0.94 or 94% of the original energy ET. And so this means that a half k a naught squared e to the minus b into t plus the period over m is equal to 0.94 into a half k a naught squared e to the minus bt over m. And so simplifying this, we get e to the minus b times the period, capital T over m, is equal to 0.94. And from here we get b over 2m is equal to minus 1 over 2t times the natural log of 0.94, which is simply minus the resonance frequency omega naught over 4 pi times the natural log of 0.94. Now f, or f prime, the frequency minus the natural frequency f naught over the natural frequency f naught is equal to 1 over 2 pi times the square root of omega naught squared minus b squared over 4m squared minus omega naught over 2 pi all over omega naught over 2 pi. And this becomes the square root of 1 minus b squared over 4m squared omega naught squared, all this minus 1. And so from the expression above, we can substitute this in for b over 2m, and we get this to be the square root of 1 minus the natural log of 0.94 all squared divided by 16 pi squared, all of this again minus 1. So we can approximate this, and this is equal to 1 minus a half into the natural log of 0.94 squared divided by 16 pi squared minus 1. And so this is minus a half. We can see 1 minus 1 is equal to 0. That's minus a half times the natural log of 0.94 all squared over 16 pi squared. And so if we calculate this, we get this to be minus 1.2 times 10 to the minus 5. So therefore, as a percentage difference, this is equal to f prime minus the natural frequency f naught divided by f naught simply multiplied by 100. So this is equal to minus 1.2 times 10 to the minus 3 as a percentage. And that's our first answer, the percentage that the frequency differs from the natural frequency f naught. Now for part B, we want to know the number of periods that will pass until the amplitude will have decreased to 1 over e of its original value. Now the amplitude's decrease in time is given by the equation A is equal to a naught e to the minus bt over 2m. So we need to find the decrease at a time of n times capital T, where capital T is the period. And then we can solve for n, the number of periods. And so using the value of b over 2m that we found in part A, we have this expression for the amplitude A. And from here we can see that a naught e to the minus 1 is equal to a naught e to the minus b n t divided by 2m, which means that 1 is equal to b. 1 is equal to b over 2m times n times t. And so using the expression above, this is minus 1 over 2t times the natural log of 0.94 times n times t, which means we can rearrange and solve for n, the number of periods, to be minus 2 over the natural log of 0.94. And so calculating, we get this to be 32.32, or simply 32 periods.